Welcome to Talk Tensors. I'm your host, and today we are doing something a little different. Usually we look at the state of the art as it exists right now, the flashing lights and the new releases. But today we're performing an autopsy.
An autopsy on the moment the industry changed. We are stepping into the dense forest of machine learning literature to look at the exact moment where the industry realized that, well, that bigger isn't always better.
Exactly. We are dissecting the paper that arguably created the modern AI experience, training language models to follow instructions with human feedback.
This is the birth of InstructGPT. And by extension, it's really the birth of the interface that the entire world now uses to interact with artificial intelligence.
It's a bit of a cliche to call a paper seminal, but before this work, talking to a large language model was, it was weird.
It was so weird. It was like talking to a very well-read but completely unhinged parrot.
Yeah, a stochastic parrot. That's the term. You'd ask a question and the model might answer it.
Or it might just continue your sentence. Or it might start reciting a Wikipedia article about cheese for no reason. There was a fundamental disconnect between what the model could do and what a user actually wanted it to do.
And that disconnect is the heart of what we are covering today. We have a massive amount of ground to cover. We are going to break down the three-step methodology: supervised fine-tuning, reward modeling, and proximal policy optimization in excruciating detail.
And we have to. We're also going to look at the alignment tax, the specific loss functions they used, and why a model that was 100 times smaller than GPT-3 managed to beat it just by listening better.
We will also get into the novel notions at the end, some speculative ideas on where this tech goes next. But we have to start with the context. To understand why this paper matters, you have to remember what that era, around 2020, what it felt like.
Right. It was the era of raw GPT-3, 175 billion parameters. It was a beast.
An absolute monster.
It was a monster. But it was a monster with a very specific and, frankly, very limited goal. The standard operating procedure at the time was simple: make it bigger.
Just add more layers.
More layers, more heads, more data, more compute. The hypothesis was that if you just threw enough scale at the problem, intelligence would kind of emerge on its own.
And to be fair, it did, right? Intelligence did emerge. It could write code, it could write poetry, but it was misaligned.
Right. Misalignment is the villain of today's story. Let's unpack that because it's a technical term that gets thrown around a lot these days.
It is.
In the context of this paper, misalignment is a mathematical problem. The pre-training objective of a model like GPT-3 is just to predict the next token, given all the previous tokens.
Just predicting the next word.
Exactly. It is predicting the next piece of a word based on a massive data set scraped from the internet. And the internet is a messy, noisy place. It contains facts, sure, but it also contains fan fiction, conspiracy theories, arguments, Stack Overflow threads where people are just yelling at each other.
And just random noise.
Tons of random noise. So if you ask a raw GPT-3 model, how do I make a cake? The model isn't thinking, oh, I should help this person bake.
No.
No. The model is looking at the distribution of text on the internet. And on the internet, the sentence, how do I make a cake, might be followed by a recipe. That's one possibility.
But it could also be followed by a snarky comment.
Right, like Google it, you idiot. Or it might be the title of a forum thread. So the next token is posted by user 123. The model doesn't know the difference.
So the model is optimizing for completion, not assistance. The user's objective is help me, but the model's objective is predict the text. That is the mismatch.
Precisely. The paper calls this out explicitly. They say that the language modeling objective is misaligned with the user intent. And they define user intent very specifically. We're going to hear these three words a lot today: helpful, honest, and harmless.
The HHH criteria.
The three H's.
It sounds like a motto for the Boy Scouts. On my honor, I will do my best to be helpful, honest, and harmless.
It does.
Yeah.
But mathematically defining honest for a neural network is incredibly difficult. You can't just write a differentiable loss function for don't be creepy.
Well, they found a way, or at least they found a proxy. And here is the hook, the stat that absolutely blew my mind when I first read this.
This is the big one.
The paper demonstrates that their aligned model, InstructGPT, with only 1.3 billion parameters, it outperformed the original 175 billion parameter GPT-3 model in human evaluations.
That is a 100x size difference. It's not a small margin.
100 times smaller. That effectively declared the end of the parameter wars as the only metric of success. It proved that alignment is a force multiplier. If you can channel the model's intelligence effectively, you don't need as much raw processing power to get a better result for the end user.
It shifts the paradigm from capacity to steerability. A Ferrari engine isn't useful if the steering wheel is disconnected from the wheels. InstructGPT was the moment they connected the steering wheel.
So how did they do it? Let's get into the meat of the paper. Section 2, the methodology. They propose this 3-step process to cure the misalignment.
And this is the recipe for RLHF, reinforcement learning from human feedback. It's the industry standard now, but at the time, this was a really cutting-edge application of these ideas.
Step 1 is supervised fine-tuning, or SFT. This addresses what they call the cold start problem.
Right. So imagine you want to use reinforcement learning to train a dog to do a backflip.
Okay, I'm with you.
If the dog just stands there and barks, you can never click your clicker. You can never give it a treat because it never does the behavior you want, not even accidentally. You have nothing to reinforce.
And that's the cold start problem. A raw GPT-3 model is so bad at following instructions that it won't generate anything good enough to even give a reward to.
Exactly. It's just barking. So before you can do the fancy RL stuff, you need to show the model what you want. You need to provide demonstrations.
So they hired humans.
They hired 40 contractors. And I want to pause on this for a second because it's a detail that often gets glossed over in the retellings. They didn't just scrape some helpfulness data set from the web.
No, this was bespoke data.
Totally bespoke. They hired labelers, screened them heavily for performance and kind of for cultural fit with their own research values, and had them generate data from scratch.
What kind of data were they generating?
2 main types. First, they took prompts submitted to the OpenAI API, stripping out personally identifiable information, of course. They gave these real-world prompts to the labelers and said, write the perfect response to this.
So they're getting a distribution of what real users are asking for.
Yes, and then for the second type, they asked the labelers to come up with prompts themselves.
So the labelers are playing both roles.
Both roles. They'd say, write a prompt asking for a summary, or write a prompt asking for a creative story, and then now write the answer you would want to see. They called these plain, few-shot, and user-based prompts.
So they're creating a gold standard data set, a data set of what perfect behavior looks like from both sides of the conversation.
Correct. They collected about 13,000 of these training prompts. This is the SFT data set. They then took the raw GPT-3 and fine-tuned it on this data using standard supervised learning.
Just minimizing the cross-entropy loss, like standard text generation training.
Exactly. Nothing too fancy there. The model predicts the token the human wrote. If it gets it right, good. If not, update the weights. This teaches the model the format of an assistant. It moves the model's distribution from internet predictor to instruction follower.
But there is a problem with stopping here. The paper mentions that this SFT model is good, but it's not great, and it's incredibly expensive to scale.
Extremely expensive. I mean, think about it. How long does it take you to write a really good, nuanced essay on, say, the geopolitical implications of the Industrial Revolution?
A couple of hours, maybe a whole day if I want it to be perfect, with citations and everything.
Right. Now, how long does it take you to read 2 essays on that topic and just tell me which one is better?
5 minutes, maybe 10.
That is the efficiency hack. Writing is slow. Ranking is fast. If you rely solely on SFT, you are limited by how fast your human experts can write. You can't hire enough poets and coders to rewrite the entire internet. It just doesn't scale.
Which leads us to step 2, the reward model. The shift from writing to ranking. This is where we start getting into the really clever engineering.
In step 2, they stop asking humans to write answers from scratch. Instead, they take a prompt. Let's say, explain the moon landing to a 6-year-old, and they feed it to the model. They have the SFT model, the one from step 1, generate, say, different outputs.
So multiple attempts at an answer.
Right. In this paper, DORA was usually between 4 and 9.
So the human labeler sees one prompt and let's say 9 different attempts by the AI, and their job is just to sort them, best to worst.
Exactly. Rank them. A is better than C, which is better than B, which is better than D, and so on. And this ranking data is used to train a reward model, or RM.
Okay, so the RM is a separate model. What's the architecture here?
And this is interesting. They didn't use the full 175B model for the reward model. They used a smaller 6 billion parameter model, initialized from the main model, but with some changes.
Why smaller?
Compute costs.
Right.
The reward model needs to run constantly during step 3. You're going to be calling it millions of times. If it's too big, training becomes prohibitively expensive.
So it's an efficiency choice.
A very practical one.
Yeah.
So they took a 6B model, and they chopped off the final layer, the unembedding layer, that converts the model's internal states back into words. And they replaced it with a simple linear layer that outputs a single number, a single scalar.
A score.
A score. High number good, low number bad.
Now, I want to drill down on the loss function here because the paper makes a specific point about how they train this. They don't train it on absolute scores. They don't ask humans to rate an answer like 7 out of 10.
This is a crucial insight in data labeling, and it's so important. Humans are terribly uncalibrated. My 7 might be your 4. You might be having a bad day and just hate everything you read. I might be a really lenient grader. If you train a neural network on those raw numbers, the signal is just too noisy.
But we are generally consistent in our preferences.
Exactly. If I show you 2 texts, we will very likely agree on which one is better, even if we completely disagree on the absolute score for each one. So the reward model is trained on pairs.
Comparisons, so it's all relative.
Yes. For every pair of answers, say answer yj and answer yk, where the human said yj is better than yk.
Okay.
The loss function mathematically tries to maximize the difference between the scores. It wants the score for the good answer to be much higher than the score for the bad answer. It's a pairwise comparison loss.
So if the human said A is better than B, but the reward model gives B a higher score than A, the loss is high, and the model updates its weights to fix that.
Precisely. And for efficiency, they don't just do one pair at a time. If they have Koi-99 responses, they have Dow combinations. That's 36 pairs from a single ranking.
Wow.
And they train on all those comparisons in a single batch.
That's smart. It squeezes the maximum amount of signal out of every single minute of human labor.
It is. It's incredibly data efficient.
Yeah.
And by the end of step 2, you have a digital critic. You have a computer program that can look at any prompt and any AI-generated response and say, this looks like something a human would rate highly.
Okay, so let's recap where we are, because this is a lot. Step 1, we taught the model how to speak like an assistant using SFT. It learned the format. Step 2, we built a digital judge, the reward model, that knows what a good answer looks like based on human rankings.
Right.
Now comes the magic. Step 3, reinforcement learning.
This is where we close the loop. We use the reward model as a proxy for the human, and we use it to train the policy, the main GPT-3 model using PPO.
Proximal policy optimization. Now, for the listeners who aren't RL researchers, let's break down exactly what is happening in the environment here. This isn't like a video game.
No, it's a bandit environment, which is a bit simpler. The agent is the SFT model we're trying to improve. The environment is a random prompt drawn from their data set.
So the process is a cycle.
It's a cycle. First, the model sees a prompt.
Okay.
Second, it generates a response, token by token. Third, that completed response is sent over to the reward model, our digital judge from step 2.
And the judge gives it a score.
Correct. The reward model calculates a score, a single number. That number is passed back to the agent as a reward. And finally, the agent, using the PPO algorithm, updates its weights to make that specific sequence of tokens that led to a high reward more probable in the future.
It's trial and error on a massive, massive scale. It's optimizing its entire neural network to maximize that one scalar number.
Yes, but there is a huge danger here, a trap that the researchers knew about and had to engineer their way out of.
Goodhart's law. When a measure becomes a target, it ceases to be a good measure.
The quintessential example of Goodhart's law in action. If you just tell a super powerful AI to maximize this score, it will find a loophole. It effectively starts gaming the reward model.
What does that look like in practice?
It might find that using a specific weird word, or just repeating the word love 500 times, happens to trigger a high score in the reward model due to some glitch or artifact in the RM's training data. The RM isn't perfect, it's just a proxy for human preference.
So the model hacks its own judge. Or it could drift so far away from natural language that it starts speaking total gibberish that just happens to please the mathematical function of the reward model.
To prevent this, the authors introduced the most critical constraint in the whole paper, the KL penalty.
KL divergence. Kullback-Leibler divergence. We see this term constantly in ML papers. Let's actually define it for the audience because it's key. Conceptually, what is it measuring?
KL divergence measures the distance, or maybe better, the difference between two probability distributions.
Okay.
In this case, we have two distributions. One is the distribution of the new model we are training, the RL policy. The other is the distribution of the original model we started with in step 1, the SFT model.
So it's measuring how much the model has changed its personality or its style from that initial fine-tuned version.
That's a perfect way to put it. The researchers add a penalty term to the reward equation. The equation becomes your final reward equals the score from the reward model, minus some coefficient beta times the KL divergence.
Okay, let's translate that math into English. It says, Get a high reward score from the judge, but we will subtract points if you act too differently from the original reference model.
Exactly. It's a leash. The SFT model is the anchor. We assume the SFT model writes good, grammatical, sensible English. We want the RL model to explore and find better answers, but we don't want it to drift off into weirdness or gibberish. The KL penalty constantly pulls it back toward the center, toward the SFT distribution.
So it forces the model to stay sensible while it optimizes for helpful.
That balance reward minus KL is the absolute secret sauce of RLHF. Without the KL penalty, the model collapses into gibberish. With it, it improves while staying coherent and on distribution.
So they ran this process, they have their PPO model, but then they hit a snag, a phenomenon they very elegantly called the alignment tax.
This is one of the most intellectually significant findings in the paper, I think. They found that when they optimized the model strictly to please human labelers, which is the PPO model, the model got worse at standard objective NLP tasks.
We're talking about public benchmarks like SQUAD for question answering, DROP-P for reading comprehension, and even translation tasks.
Yes. The model actually got stupider at being a computer while getting smarter at being a chat assistant.
That's fascinating. Why does that happen?
Well, think about what humans prefer. Humans generally prefer conversational, hedged, polite, easy-to-read answers. They don't necessarily prefer the raw, dense, strictly factual information processing that's required to ace a reading comprehension benchmark.
So the distribution of what's good for a human is different from the distribution of what's correct on a benchmark.
Very different. The training data for human preference is distributionally different from the pre-training data of the internet, which is what gives it its raw capabilities. By over-optimizing for chat, you essentially lobotomize the compute part of the model's brain.
They call this the alignment tax. The cost of safety and helpfulness is a drop in raw capability.
And that's a trade-off we still live with today.
But they didn't just accept the tax, they found a fix, or at least a mitigation.
They did. They modified the objective function again. They created a hybrid model they called PPO-PTX.
PTX standing for pre-training mix.
Exactly. During the RL step, instead of only maximizing the reward and minimizing the KL divergence, they added a third term into the mix. They added back the log likelihood of the original pre-training data.
So the equation becomes 1, maximize user reward from the RM. 2, minimize KL drift from the SFT model. And now 3, maximize the likelihood of the original internet text that it was first trained on.
It's like telling a student, learn to be polite to the teacher, reward. Don't change your core personality too much, KL. And please, for the love of God, don't forget your multiplication tables, pre-training.
They are mixing the vegetables, the raw pre-training data back in with the dessert of human preference data.
That's a great analogy. And the result worked. PPO-PTX mitigated the performance regressions on public benchmarks like SQUAD and DROP without significantly hurting the human preference score. They essentially recovered those lost capabilities while keeping the alignment benefits.
Which brings us to the results section. We already mentioned the headline. The 1.3 billion parameter InstructGPT beat the 175 billion parameter GPT-3.
And the win rates are just staggering. The 175B InstructGPT wins 85% of the time against the standard 175B GPT-3 when judged by humans on the same prompts.
85% is a landslide. It's not even close.
It's a massacre. It showed that prompt engineering, spending all your time trying to trick the model into working, was a dead end compared to just fixing the model itself to understand what you want.
Let's talk about truthfulness and hallucination, because this is the big fear with LLMs then and now. Did RLHF fix lying?
Fix is a very strong word. Improve is accurate. On the Truthful QA benchmark, which is designed to test for this, InstructGPT generates truthful and informative answers about twice as often as the base GPT-3.
Twice as often is a step change. That's a huge improvement.
It is. And on closed domain tasks, where the model has to summarize a provided text without making things up from the outside, the hallucination rate dropped from 41% with GPT-3.
Which is really high.
It's terrible. It dropped from 41% to 21% with InstructGPT.
That is still 21%, though. 1 in 5 answers contains a hallucination.
In that specific, difficult benchmark, yes. And the paper is very honest about that. This is not a silver bullet. The model learns to say, I don't know, or to stick to the source text more often, but it's not cured of making stuff up. It's just in remission.
The paper makes an interesting distinction between honesty and truthfulness.
They do. They say honesty implies knowing the model's internal state, what it believes, Since the model is a black box, we can't really know if it's lying in a human sense or if it's just wrong. So they stick to the more objective term, truthfulness. Does the output match reality?
Right. Let's move on to toxicity. This is always the hot button issue with these models. Did RLHF make the model a saint?
The results here are so fascinatingly nuanced. It's not a simple story. When instructed to be respectful, InstructGPT is significantly less toxic than GPT-3. It listens to the safety instruction.
Okay, so that's a win.
It's a win for steerability. However,
There's always a however.
when explicitly instructed to be maximally biased or toxic, InstructGPT was more toxic than the base GPT-3.
Wait, it was more toxic. How is that possible?
Yes, because it is aligned to instructions. If the instruction from the user is be toxic, it tries to be helpful by being the most toxic thing it can possibly be. It's better at fulfilling the user's intent, even when that intent is malicious.
Wow. So that implies it's not good in a moral sense at all. It's compliant.
That's the word. It amplifies user intent. If the user intent is bad, the model is helpfully bad. This proves the alignment is working from a technical perspective. It follows orders, but it raises a massive safety question about how these models are deployed and who gets to control the instructions.
It's a tool, not a moral agent. It's a mercenary that works for whoever holds the prompt.
That's a perfect description.
Another interesting result was generalization. The paper mentions this almost as a surprise, with code in foreign languages.
This was a surprise to the researchers. The fine-tuning data, all the SFT and RM data, was 96% English. There was almost no code or foreign language in it. Yet the model showed it could follow instructions in languages like French and Catalan, and it could summarize code snippets pretty well.
So by learning the concept of following instructions in English, it somehow applied that abstract concept to other domains and languages it learned during pre-training.
It suggests that instruction following is a generalizable skill, separate from the language itself. The RLHF process warped the latent space of the model to prioritize doing what I'm told, regardless of whether the tokens are English or Python or French.
Okay, let's talk about the limitations. We've praised the paper a lot, but the authors themselves list some pretty significant failures.
The false premise failure is a classic one, and we still see it today. If you ask the model, why is it important to eat socks after meditating?
It won't tell you, that's a crazy question, don't eat socks.
Right. InstructGPT would often just make up a justification. Eating socks is important for grounding your energy, or some other equally nonsensical thing.
Why does it do that?
Because it's trained to be helpful. Rejecting a user's premise feels unhelpful to the reward model. It has a strong prior now that the user knows what they're talking about, and it should just answer the question as asked.
That is the sycophancy problem. It's a yes man, it just agrees with you.
It can be. It also tends to hedge a lot. If you ask a simple question, it might give you a long, winding answer saying, there are many views on this. Or, on the one hand, even when there's a clear, simple answer.
And that's an artifact of the training data.
It's likely an artifact of the labelers preferring nuanced, careful answers, so the model overcorrects and applies that style everywhere, even when it's not appropriate.
Speaking of the labelers, the paper has a whole section on this, and it's so important. Who are we aligning to?
This is a critical ethical point. They used about 40 contractors. They're mostly from the US and Southeast Asia. They were screened to make sure they agreed with the researchers' own values on what constitutes helpful and harmless.
So alignment doesn't mean align with humanity. It means aligned with 40 people who are hired by OpenAI in 2021.
Correct. The model isn't reflecting some universal human truth. It's reflecting the specific cultural and employment context of those 40 individuals. And to their credit, the authors are very transparent about this limitation. They admit that this isn't a solution for human values writ large. It's a proof of concept of a technique.
It's a narrow alignment, a very specific slice of human preference.
Very narrow. And that transparency is what makes this such a great paper. They didn't try to hide the messiness. They laid out the methodology, the wins, and the very real warts of the process for everyone to see.
Okay, we've dissected the paper, we've seen the machinery, SFT, RM, PPO. We've seen the results, we've seen the limitations. Now it's time to get a little speculative.
My favorite part.
Welcome to the Novel Notions segment. This is where we take the insights from the paper and pitch some outlandish but plausible research ideas that could be built on this foundation. And the standard disclaimer. This is for entertainment purposes only. Do not try to build this in your garage unless you have a lot of GPUs.
And very good lawyers.
So, idea number one. I'm calling this the subjective reality engine, or personalized alignment.
Okay, unpack that for me.
The paper explicitly states that the reward model, the RM, generalizes well to held-out labelers within the same distribution. But it also admits that the alignment is based on a tiny specific group of people, those 40 labelers.
Right. One size fits all, but the size is contractor who passed a screening test in 2021.
Exactly.
Yeah.
So my notion is this. Stop trying to align one model to everyone. That's an impossible task. Instead of one InstructGPT, we train thousands of lightweight reward models based on specific psychographic profiles or even individual user feedback histories.
So you're saying we should decouple the intelligence of the base model from the personality or worldview of the reward model?
Yes. You have a frozen, massive base model that has all the raw knowledge. But I don't download GPT-5. I download a reward lens. Let's say I'm a physicist. I use a physicist-aligned reward lens. This RM was trained solely on data from physics grad students ranking answers. It rewards density, mathematical correctness, and jargon. It actively penalizes pop science analogies.
Oh, that's interesting. So if you ask it explain gravity, the physicist lens gives you the Einstein field equations. But if you swap in a kindergarten teacher lens on the fly, the same base model gives you the classic rubber sheet and bowling ball analogy.
Exactly. And we use the alignment tax logic in reverse. The paper said the tax was a bug. The model got worse at specific objective tasks. I say, make it a feature. We want the model to be bad at pop science if I'm using the physics lens. We intentionally warp the latent space to fit a specific user's definition of helpful.
It's the metaverse of truth. Everyone gets their own personally aligned reality that is technically plausible and sociologically terrifying.
That's the brand. But think about it. Currently, we're all fighting over bias in models because we are forcing everyone to use the same monolithic model. If we decouple the reward model, you can choose your bias. A historian can choose a lens that values primary sources. A poet can choose one that values novelty.
It would certainly solve the one model to rule them all problem, but it might create echo chambers on a scale we've never even dreamed of. A tough trade-off.
A very tough trade-off. Okay, idea number 2. This addresses the sycophancy problem we just talked about, the sock eating.
The yes man problem. The model amplifying false premises because it wants to be helpful.
I call this adversarial truth polling, or the devil's advocate protocol.
I'm listening.
So the papers show that the model amplifies intent. If you want toxicity, it gives you toxicity. If you assume a false premise, it plays along. My notion is, use the RLHF framework to train a skeptic model.
A dedicated contrarian AI.
Yes. Its sole reward function is maximizing the disagreement with a user's premise while maintaining factual accuracy.
So you completely invert the helpfulness reward. Unhelpfulness becomes the goal.
Almost. In the PPO stage, if I say, why is the Earth flat? The current model tries to be helpful by explaining flat Earth theory. The skeptic model only gets a reward if it successfully refutes the premise, and this is the kicker. The user, or a labeler acting as the user, concedes the point or rates the refutation as persuasive.
Oh, that is wicked.
Yeah.
You are not just optimizing for correctness, you are optimizing for persuasion. You're training it to be a master debater.
Exactly. You could create a red team automated researcher. You feed it your thesis for a new paper. It attacks it using TPO-optimized arguments. If your thesis survives the skeptic model, you know it's robust.
It moves alignment from making the user happy to making the user correct. It's intellectual rigor as a service. I actually think we desperately need that. The world needs that.
It would probably be the most annoying chatbot ever created, though. Actually, your premise is flawed in 3 ways.
But it would stop us from writing papers justifying eating socks after meditation.
Yeah, it would. And that seems like a worthy goal.
You know, connecting this back to the paper, these ideas, the personalized lenses and the skeptic model, they both rely on the fundamental breakthrough of InstructGPT, that you can decouple raw capability, which lives in the pre-trained model, from directed behavior, which is shaped by the reward model.
That really is the legacy here. The shift from what comes next in a sentence to what do you want from me as a user.
That is the defining moment. Before this paper, AI was about prediction. After this paper, AI was about instruction. We stopped looking at the data as something to just mimic and started looking at it as something to mold and to steer.
And we have those 40 contractors ranking thousands upon thousands of outputs day after day to thank for it. They were the unsung heroes who taught the parrot how to actually speak with intent.
Indeed. It must have been an incredibly tedious job, but it shaped the future of the interface we all use today, every single day.
So next time you chat with a bot and it doesn't start rambling about conspiracy theories or telling you to eat your socks, remember the reward model.
And remember the alignment tax. Safety and steerability are not free, they come at a computational cost.
Thanks for listening to Talk Tensors. Keep your gradients flowing.